There's a quiet cosmic mystery that could change everything we know about the universe. For decades, scientists believed the cosmos was uniform, that on the largest scales, matter was evenly spread out. But new evidence suggests our region of space might be far from average. Some astronomers now think we're living inside a cosmic void, a gigantic, underdense region billions of light years wide. If true, this means our cosmic neighborhood is emptier than we ever imagined, and it could even change how we measure the universe's expansion and its age. We might be sitting inside a vast cosmic hole, and only now are we starting to realize it. And if you want to uncover the full story, then watch this video till the end and subscribe to the channel. Let's begin. If we really are inside a vast emptiness, the next question becomes, what exactly is a cosmic void? In the grand design of the universe, matter isn't spread out evenly. Instead, it forms an intricate cosmic web, an enormous network of filaments made of galaxies, clusters, and dark matter. Between these luminous threads lie immense, dark gaps known as cosmic voids. These are enormous regions of space containing far fewer galaxies, less gas, and a much lower overall density than the cosmic average. Voids can span anywhere from tens to hundreds of millions of light years across, with some giants stretching even further. Within them, the few galaxies that do exist are often small, faint, and isolated. Cosmic islands adrift in seas of nothingness. These regions aren't truly empty, of course. They still contain dark matter and thin traces of intergalactic gas, but at densities so low, they're nearly undetectable. What makes voids so remarkable is that they're not anomalies. They're an essential part of how the universe evolved. After the Big Bang, the early universe was filled with slight density variations, tiny quantum ripples that gravity later amplified. Matter was drawn into the denser regions to form galaxies and clusters, while the less dense areas became emptier over billions of years, expanding faster and faster relative to their surroundings. The result is a universe shaped like a vast sponge, with galaxies forming the filaments and the voids forming the holes in between. So, when we talk about living inside a cosmic hole, it's not just poetic. It's quite literal. And this brings us to one of the most intriguing possibilities in modern cosmology, that our own galaxy might sit near the center of one of these enormous underdense regions, known as the KBC Void. In 2013, 3 astronomers, Ryan Keenan, Amy Barger, and Lennox Cowie, proposed something extraordinary. While studying the large-scale distribution of galaxies, they noticed a strange pattern. Our cosmic neighborhood seemed to contain fewer galaxies and less matter than expected. Their research suggested that we might be living inside a massive underdense region of space, a vast cosmic void that would later become known as the KBC Void, named after its discoverers. This wasn't a small local dip in density. The KBC Void, according to their measurements, could be one of the largest structures in the observable universe. So large, in fact, that it challenges what cosmologists once thought possible. Keenan and his colleagues used observations of galaxy surveys and supernova data to map how matter is distributed around us. They found that as you move outward from our position in space, galaxy density slowly increases, like climbing out of a shallow cosmic basin. Their findings implied that the Milky Way sits near the center of this enormous underdense region. In simpler terms, our galaxy might be floating inside a cosmic bubble, surrounded by regions that are far denser and richer in galaxies. If this is true, it would mean our cosmic address isn't in an average spot in the universe at all. We might live in one of its loneliest neighborhoods. What makes the KBC Void so captivating is not just its size, but its implications. It could help explain some of the biggest puzzles in modern cosmology. including why our local measurements of the universe's expansion rate don't match those from the early universe. But before we explore that mystery, it's worth appreciating just how vast this supposed void really is, because its scale alone is enough to boggle the mind. When we talk about the scale of the KBC Void, we are speaking of something that stretches the very limits of human imagination. This isn't a small dip in the fabric of the cosmos. It's a staggering, near incomprehensible depression in the density of matter, spanning an estimated 2 billion light-years across. To put that in perspective, light, the fastest thing in existence, would take 2 billion years to cross from one side of this region to the other. By comparison, our Milky Way galaxy is just about 100,000 light-years wide, meaning this void could swallow it 20,000 times over and still have room to spare. To truly grasp this size, imagine a cosmic landscape woven from threads of galaxies and clusters, the cosmic web. In this web, filaments of matter connect into nodes where superclusters of galaxies reside, while vast spaces between them remain comparatively barren. The KBC Void is one of these enormous empty regions, but it's not like the smaller voids we find sprinkled throughout the universe. It's a supervoid, a region so immense and underdense that it dwarfs most of the structures we've ever mapped. Scientists estimate that its average density is about 20 to 50% lower than the cosmic mean, meaning there's almost half as much matter per cubic megaparsec compared to denser parts of the universe. What's even more remarkable is that this isn't a sharply defined sphere with clear boundaries. Like everything in cosmology, its edges are diffuse, a gradual transition from emptiness to fullness, from cosmic desert to cosmic metropolis. As one travels outward from our position within the KBC Void, galaxy density increases slowly, blending into the richer cosmic filaments that define the observable universe. In this sense, the void isn't just an absence of matter. It's a gradient, a smooth dip in the universe's density field that subtly warps how space itself expands. And that expansion is the key. In lower density regions like the KBC Void, gravity exerts less pull. That means space within the void expands faster than in denser areas. Not enough for us to feel locally, but enough to influence our measurements of distant galaxies. This has profound consequences for how we interpret astronomical data, especially when we use light from faraway supernovae and galaxies to estimate the rate at which the universe is expanding. In essence, being inside such an enormous underdense region could make the cosmos appear to be expanding faster from our vantage point than it actually is on average. This subtle bias might even help explain one of the greatest puzzles in modern astrophysics, the mysterious Hubble tension, which we'll get to later. But even setting aside its cosmological implications, the sheer scale of the KBC Void is enough to give one pause. 2 billion light-years is roughly 1/10 the diameter of the entire observable universe. It's not a localized feature. It's a structure that competes with the largest known cosmic phenomena, like the Sloan Great Wall or the Hercules Corona Borealis Great Wall, which are vast chains of galaxies spanning similar distances. Yet, while those structures are made of something, colossal threads of galaxies and clusters, the KBC Void is defined by what it lacks. It's an emptiness so huge that, if you could visualize it, it would look like a vast cosmic cavern surrounded by glittering walls of galaxies stretching out in every direction. To further appreciate its immensity, consider this. The Virgo supercluster, which contains the Milky Way and our neighboring galaxies, is about 110 million light-years wide, enormous by any normal standard. But the KBC Void could contain nearly 20 Virgo superclusters side by side and still not be filled. That's how vast and gaping this region is. If you could somehow fly across it at near light speed, it would still take billions of years to traverse. What's more, Such a vast underdense region challenges the assumptions at the heart of cosmology, namely the cosmological principle, which states that on large scales, the universe is homogeneous, the same everywhere, and isotropic, the same in all directions. The KBC Void pushes against this principle, hinting that perhaps our cosmic neighborhood is not as typical as we once thought. If we truly live near the center of this immense void, it would make our location rather special, something cosmologists have long resisted since modern science has strived to remove Earth and humanity from any privileged place in the cosmos. However, there's growing evidence that this vast structure is not just a statistical fluke or observational illusion. Multiple surveys, including infrared observations, redshift data, and large-scale galaxy counts, have independently suggested that the density of galaxies within about 1 to 2 billion light-years of us is noticeably lower than what would be expected if the universe were perfectly uniform. This strengthens the idea that we may indeed reside within a region of space that's subtly emptier than the cosmic average. Of course, emptier doesn't mean devoid of wonder. Even within a void, galaxies exist. Sparse, lonely systems adrift in a quiet sea of darkness. These galaxies evolve differently from their counterparts in dense clusters. Without frequent gravitational interactions or galactic collisions, they tend to be smaller, with slower rates of star formation. Studying them provides a rare window into a quieter, more isolated mode of cosmic evolution, a glimpse of how galaxies might develop when left undisturbed for billions of years. So when we say the KBC Void stretches for 2 billion light-years, we're not just describing a number. We're describing a colossal feature of the universe that redefines what it means to be local. The scale of this structure is enough to bend light, to bias measurements, and perhaps even to warp our perception of cosmic time itself. It's a gentle depression in the fabric of the universe so vast that it may subtly distort the way we see the cosmos. And at the heart of that vast emptiness, remarkably, improbably, sits our own galaxy, the Milky Way. This raises an astonishing question. What does it mean that we are at the center of one of the largest voids ever discovered? Is this mere coincidence, or could it have shaped our very understanding of the universe's expansion? That's where the story takes its next fascinating turn, because according to the KBC hypothesis, our position inside this gigantic void might hold the key to one of cosmology's greatest ongoing mysteries. According to the KBC Void hypothesis, our own Milky Way galaxy, along with everything we can observe from our vantage point on Earth, lies near the center of this immense underdense region. That's right, we might be floating right in the middle of one of the largest cosmic voids ever proposed. This idea sounds almost heretical in modern cosmology, because for centuries, scientists have fought to remove humanity from any notion of being central in the universe. From Copernicus to Hubble, each scientific revolution has reminded us that we occupy no privileged place. Not at the center of the solar system, not at the center of the galaxy, and certainly not at the center of the cosmos. Yet, paradoxically, evidence from astronomical surveys hints that, on the largest scales, our cosmic address might indeed lie within the calm heart of a vast cosmic depression. To understand what this means, imagine the universe as a three-dimensional web of matter, filaments of galaxies and clusters stretching across space, intersecting at dense nodes and separating great hollow regions. Now, place the Milky Way not along one of those bright filaments, but inside a gigantic bubble in between. When scientists map out the distribution of galaxies around us using redshift surveys, which measure how much the light of distant galaxies is stretched by cosmic expansion, they see that galaxy counts gradually increase as we look farther away. In other words, our local universe appears slightly emptier than regions lying beyond a radius of roughly 1 to 2 billion light-years. That slow rise in density fits perfectly with what one would expect if we were sitting near the center of a vast void. From our perspective, galaxies beyond the edges of this underdense region would appear more tightly packed. Their light would also be slightly redshifted due to the higher expansion rate inside the void, giving us the illusion that the universe is expanding faster nearby than it does farther away. This spatial gradient isn't something we can feel or see directly, but it manifests in the data, shaping the very constants we use to describe the cosmos. Now, being at the center of the KBC Void doesn't mean we're sitting in some literal geometric midpoint, like the eye of a hurricane. The void isn't a perfect sphere, and its boundaries are diffuse rather than sharp. The idea is that the Milky Way resides within the most underdense portion of this vast depression, where the density contrast, the difference between the local density and the cosmic average, is at its lowest. We're effectively surrounded by regions that gradually grow denser in every direction. That's why, from our perspective, the universe looks roughly uniform, because we're in the middle of a gradient, seeing the same slow climb in galaxy density wherever we look. But why is our position within this void so important? Because it subtly alters how light from distant galaxies reaches us. Imagine tossing pebbles into a still pond. In the deep parts, the ripples move differently than near the shallow edges. Similarly, the way space expands inside a low-density region differs from how it expands in denser surroundings. Light from galaxies near the void's edges must travel through regions expanding at different rates before it reaches our telescopes. This can slightly distort our perception of distances, making galaxies seem farther away than they really are, or appear to recede faster. These distortions feed directly into one of the most puzzling measurements in cosmology, the Hubble constant, which describes how fast the universe is expanding. The idea that our galaxy might sit near the center of a structure 2 billion light-years wide is as humbling as it is provocative. It doesn't imply any special cosmic significance. Instead, it reminds us how incomplete our perspective still is. For most of human history, our understanding of the cosmos has been shaped by what we can see, yet the universe's largest structures are so vast that even light takes eons to reveal them. The KBC Void hypothesis invites us to reconsider our place not just metaphorically, but physically, as inhabitants of an unusually empty patch of the cosmic web. Living inside a void could help explain why the local universe seems to behave slightly differently from the cosmos as a whole. Measurements of nearby galaxies, supernovae, and the cosmic expansion rate all appear subtly biased compared to the predictions made from early universe observations, such as those of the cosmic microwave background. Perhaps that bias isn't because our measurements are wrong, but because our environment, the part of the universe we occupy, is different from the average. Of course, this notion unsettles the long-held cosmological principle, which assumes that the universe is homogeneous and isotropic on large scales. If our local region is this underdense, then our cosmic neighborhood isn't average at all, and the assumption of uniformity begins to wobble. For decades, cosmologists treated this principle as a cornerstone of modern theory, but discoveries like the KBC Void force us to revisit that foundation. Are we really typical observers of the cosmos, or do we live in a special place after all? It's a tantalizing possibility. If the Milky Way truly rests in the center of a supervoid, then our entire view of cosmic expansion, dark energy, and large-scale structure might be slightly skewed by our vantage point. In other words, what we see when we look out into space could depend not only on when we're observing, billions of years after the Big Bang, but also on where we're observing from. The KBC hypothesis doesn't claim we are unique in a metaphysical sense, but it does challenge the comfortable assumption that our location is cosmically average. We might not be the center of everything, but perhaps we are the calm eye of an enormous, invisible storm, a rare place of relative emptiness adrift in a universe filled with grand structures. This leads us naturally to the next question. Why does this matter? What difference does it make if we're sitting inside a cosmic void rather than an average region of space? As it turns out, this subtle difference could have profound consequences for how we interpret nearly every major cosmological measurement, from the apparent rate of cosmic expansion to the mystery of the Hubble tension that continues to divide astrophysicists today. Understanding why this matters begins with realizing just how dependent our entire view of the universe is on our vantage point. When astronomers look out into space, they're not merely observing what's out there. They're seeing the universe as filtered through the lens of where we are. Every measurement we make, from how fast galaxies are moving to how far away they are, depends on light traveling through the vast cosmic structures between them and us. If those structures, including the very space we inhabit, are unusual, our observations may be subtly distorted. And if we truly live inside the KBC Void, one of the largest known underdense regions in the cosmos, then this distortion might not be subtle at all. At its core, the issue comes down to the expansion of space itself. In the standard cosmological model, the universe expands uniformly on large scales. Galaxies move away from one another as space stretches, and this expansion rate is quantified by a number known as the Hubble constant. But that model assumes the universe is homogeneous, that on average, every region expands the same way. If we're inside a region with less matter than average, the rules change. Gravity is weaker in low-density regions because there's simply less matter to pull things together. As a result, space inside such a region experiences less deceleration from gravitational attraction and thus expands slightly faster than the cosmic average. That means galaxies inside or near the edge of a void appear to be receding from us faster than they would if we lived in a denser region. So when we measure their redshifts, how much their light has been stretched by the expansion of the universe, we might interpret that as a sign that the entire cosmos is expanding more quickly than it really is. This leads to a potential systematic bias. From our position in an underdense region, the local universe could appear to expand faster than the global average. This phenomenon has been proposed as one possible explanation for the so-called Hubble tension, the discrepancy between the expansion rate measured from nearby galaxies and the slower rate inferred from the early universe, using data from the Cosmic Microwave Background, CMB. In other words, the very fact that we live in an unusually empty part of the cosmos might make it seem as if the universe is racing apart faster than it truly is. The implications of this are enormous. Our measurements of cosmic distances, galaxy velocities, and even the inferred age of the universe all depend on knowing the true rate of expansion. Astronomers use standard candles, such as Type Ia supernovae, to gauge how far away galaxies are by comparing their intrinsic brightness to how dim they appear from Earth. But if light from those supernovae travels through a region where space expands at a different rate, the distance we infer could be skewed. In a void, where expansion is faster, distant galaxies would appear slightly farther away than they actually are. Multiply that effect across billions of light years, and even a small local bias can cascade into a measurable difference in our cosmic models. It's not just the expansion rate that's affected. Other key cosmological quantities, like the distribution of dark energy, the curvature of space, and the large-scale flow of galaxies, can all appear different if measured from inside a massive underdensity. For instance, galaxies on the far side of the void would appear to be moving away from us slightly faster than those on the near side, simply because space is stretching faster where matter is sparse. To an observer unaware of the void's existence, this could look like an acceleration in the universe's expansion, precisely the kind of acceleration that led to the discovery of dark energy in the late 1990s. Now, to be clear, the KBC Void alone cannot explain the entire observed acceleration. dark energy remains the dominant factor driving the universe's expansion. But what the void hypothesis reminds us is that local effects matter. If we misjudge our cosmic neighborhood, we risk misinterpreting global truths about the universe. A small bias in our local expansion environment could subtly warp the numbers that underpin cosmology's biggest conclusions. Another reason this matters is that it challenges one of the foundational assumptions in cosmology, the cosmological principle. This principle asserts that, when viewed on large enough scales, the universe looks the same everywhere, that no location, including ours, is special. It's a principle born from humility, one that replaced centuries of human-centered thinking. But if the KBC Void is real, if our galaxy sits near the center of a vast region that's billions of light-years wide and significantly emptier than average, then we are not in a typical location after all. Our cosmic address might be skewing our perspective in ways we haven't fully accounted for. This isn't just a philosophical issue, it's a practical one. Every cosmological model, from the lambda CDM model that describes dark matter and dark energy to the calibration of the Hubble constant, assumes homogeneity on large scales. If that assumption fails even slightly, the ripple effects could alter the conclusions drawn from decades of data. Scientists rely on statistical averages from galaxy surveys to estimate how matter is distributed, but if our position happens to lie inside a massive underdensity, those averages become locally biased. It's a bit like trying to measure the average depth of the ocean while sitting in a shallow bay. The water level around you might look low, but that doesn't mean the entire ocean is. Without realizing you're in a hollow, you might draw the wrong conclusions about the sea itself. Similarly, if the Milky Way resides in a cosmic depression, the KBC Void, we might be underestimating or overestimating universal properties depending on how we interpret our local measurements. Even more intriguingly, some researchers suggest that the KBC Void could provide partial relief to the Hubble tension. While it likely can't account for the entire discrepancy between local and global expansion rates, it could contribute to part of it, perhaps explaining why local measurements tend to be consistently higher. In that sense, acknowledging our location within a void might not solve cosmology's biggest puzzles entirely, but it could help bring the pieces closer together. So why does it matter that we might live in a cosmic void? Because in cosmology, context is everything. The universe isn't a uniform, featureless expanse. It's a complex, textured fabric of matter and emptiness. Where we stand within that fabric affects what we see, how we measure, and ultimately what we believe to be true. Living inside a massive underdensity means we're looking out at the cosmos through a subtly warped window, one that magnifies expansion, distorts distances, and reminds us that even in the age of precision cosmology, our understanding of the universe is still shaped by where we happen to be. And this leads us to one of the central tensions in modern astrophysics, a literal one, the Hubble tension. It's the growing conflict between how fast the universe should be expanding, according to early universe data, and how fast it appears to be expanding when we measure it nearby. Could our existence inside a cosmic void be the missing piece of that puzzle? In modern cosmology, few mysteries have stirred as much debate and fascination as the Hubble tension, a quiet but profound disagreement that strikes at the heart of our understanding of the universe's expansion. The term refers to a puzzling discrepancy between two different ways of measuring the rate at which the universe is expanding, known as the Hubble constant, often written as h0. On one side, we have measurements of the early universe, ancient light from the cosmic microwave background, CMB, observed by missions like Planck, which suggest a relatively slower rate of expansion. On the other side, we have local measurements, based on nearby galaxies and supernovae, that consistently point to a faster rate. The difference between the two isn't small. It's statistically significant, and it refuses to go away even as measurement techniques grow more precise. To understand why this matters, we first need to unpack how these measurements are made. The cosmic microwave background, or CMB, is the faint afterglow of the Big Bang, light that's traveled across the universe for nearly 13.8 billion years. When cosmologists analyze this radiation, they use it as a kind of cosmic fingerprint that encodes information about the universe's composition, density, and expansion history. Using the CMB, the Planck satellite team calculated a value of the Hubble constant at about 67.4 kilometers per second per megaparsec, meaning that for every megaparsec, about 3.26 million light-years of distance, galaxies move away from us at 67.4 kilometers per second due to cosmic expansion. But when astronomers measure the same quantity using more direct, local methods, by observing nearby supernovae, Cepheid variable stars, and other standard candles, they consistently get a higher value, around 73 to 74 kilometers per second per megaparsec. That may not sound like a huge difference, but in cosmology, it's enormous, and it's persisted for years despite refinements on both sides. Every attempt to resolve it, whether through recalibration, better instruments, or new analysis methods, has only reinforced the reality that something fundamental might be missing in our picture of the cosmos. Enter the void hypothesis, and specifically the idea that we might be living inside a massive underdense region like the KBC Void. If our local cosmic neighborhood is emptier than the surrounding universe, that could change the apparent rate at which galaxies near us seem to recede. In lower density regions, gravity's pull is weaker, allowing space to expand slightly faster than it does in denser areas. This means that, from our vantage point inside a void, galaxies just outside our region might appear to be moving away faster, tricking us into measuring a higher local expansion rate. In other words, our local environment might be biasing our perception of the universe's expansion. The void doesn't actually cause the universe as a whole to expand faster. It simply changes the local dynamics. Think of it like standing in a valley watching raindrops fall. From your position, the drops near the valley edges appear to be spreading out more quickly than those farther away. Not because the rain itself behaves differently, but because your vantage point is skewed by the landscape around you. In the same way, living in a massive cosmic depression could make the nearby universe look as though it's expanding faster than the global average. This possibility is incredibly intriguing because it doesn't require any new physics, no exotic particles, no modified gravity, no changes to Einstein's equations. Instead, it's a geometric, environmental effect, the idea that our position within the large-scale structure of the cosmos subtly influences the data we collect. The KBC Void, with its estimated radius of nearly 1 billion light-years and an underdensity of roughly 20%, is large enough that this bias could, in theory, account for a portion of the observed Hubble tension. However, there's a catch. The numbers don't perfectly line up, at least not yet. For the void hypothesis to fully explain the Hubble discrepancy, the underdensity would need to be deeper or larger than most cosmological simulations currently allow. Still, even a partial contribution could be meaningful. If the KBC Void increases the local expansion rate by just a few percent, that could narrow the gap between local and cosmic measurements, hinting that the tension might be more environmental than fundamental. But here's where things get even more fascinating. If the void explanation is even partially correct, it would mean that our cosmic address matters in ways cosmologists have long tried to dismiss. The Hubble tension wouldn't just be a technical discrepancy, it would be a direct consequence of where we happen to live in the cosmic web. Our location, in other words, would subtly distort our perception of universal truths. It's a humbling idea, that our entire understanding of cosmic expansion, one of the most fundamental features of the universe, might depend on something as local and specific as the density of matter surrounding our galaxy. For decades, cosmologists assumed the universe was uniform enough that such local variations didn't matter. The KBC Void challenges that comfort. It suggests that to measure the universe correctly, we must account for the uneven landscape in which we're embedded. This leads us naturally into the next piece of the puzzle, the deeper mechanics of how the Void hypothesis and Hubble's constant are connected. Because if living in an underdense region really can make the universe appear to expand faster, then understanding that relationship in detail could be the key to finally unlocking one of cosmology's most persistent and perplexing mysteries. The Void hypothesis offers one of the most elegant and conceptually grounded explanations for why we might measure a locally higher Hubble constant, the rate at which the universe appears to be expanding. It doesn't invoke any mysterious new forces or exotic particles. Instead, it relies on the simple geometry and physics of cosmic structure. The basic idea is that the universe doesn't expand uniformly everywhere at all times. Variations in density, areas that are denser or emptier than average, subtly alter the way space itself stretches. And if we happen to live in a low-density region, like the proposed KBC Void, then the space around us expands just a little faster than the cosmic average. To understand how this works, let's recall a key principle of general relativity. Matter tells space how to curve, and curved space tells matter how to move. In regions where matter is abundant, such as galaxy clusters or superclusters, gravity's pull is strong, slowing down the local rate of cosmic expansion. In contrast, in regions with less matter, like cosmic voids, there's less gravitational braking. Space there isn't pulled inward as much, allowing it to expand more freely. That difference in gravitational deceleration creates a kind of expansion gradient across the universe. Denser regions expand a bit slower, and emptier regions expand a bit faster. Over billions of years, these tiny variations accumulate, producing measurable effects in how galaxies move relative to one another. If the Milky Way resides near the center of a vast underdense region, then galaxies just beyond the edge of our void, in the denser surroundings, would appear to be receding more quickly. From our perspective, that would look like a locally higher Hubble constant. This is precisely what the KBC Void hypothesis proposes. The underdense region surrounding us, roughly 2 billion light-years across, acts like a bubble of slightly accelerated expansion. Within it, space stretches faster than in denser cosmic filaments beyond its boundary. When astronomers measure the recession speeds of galaxies, through redshift and distance relationships, they're effectively measuring how quickly space expands between us and those galaxies. If we're in a faster expanding region, the results naturally yield a higher Hubble constant. Let's make this more tangible with an analogy. Imagine a loaf of raisin bread baking in an oven, a classic illustration of cosmic expansion. The raisins are galaxies, and the dough is space itself. Now suppose that one region of the dough, near our raisin, is a bit less dense. Because it has less dough to resist expansion, that region puffs up faster than the rest of the loaf. From our raisin's point of view, all the nearby raisins seem to be moving away more quickly than expected. If you were to measure the local expansion rate inside that bubble, it would appear higher than the expansion rate measured across the entire loaf. That's the void effect in a nutshell, the illusion of a faster expanding universe caused by living inside a locally accelerated region. This phenomenon isn't just theoretical. Cosmological simulations that model large-scale structure formation show that such local variations in expansion do occur. Voids, being underdense, experience slightly faster expansion compared to their surroundings. The effect is small, typically a few percent, but if the KBC void is as large and deep as proposed, the difference could be enough to nudge the local Hubble constant upward by the amount observed in real data. This could explain, at least partially, the Hubble tension, the roughly 5 to 10% difference between the local and global measurements of the Hubble constant. In the global picture, derived from the cosmic microwave background, we see the average expansion of the universe as a whole, smoothed out over billions of light-years. But in the local picture, the one based on supernovae, Cepheid stars, and galaxy redshifts within a few billion light-years, we're essentially measuring from inside an environment that's not representative of the universal average. If our local region expands faster, it's no wonder that our measurements come out higher. However, the extent to which this effect can explain the Hubble tension is still debated. For the void hypothesis to fully resolve the discrepancy, the underdensity would have to be both extremely large and quite deep, larger and emptier than most simulations of cosmic structure predict. Current estimates suggest that the KBC Void, with a density contrast of about 20 to 30%, could account for perhaps half of the tension, but not all of it. Still, even a partial contribution would be significant because it highlights that cosmic environment matters when interpreting universal measurements. Another subtle point concerns how light travels through space. Photons from distant galaxies traverse billions of light-years before reaching us, passing through regions of varying density. Inside an underdense region, like the KBC Void, light would experience less gravitational redshift. That is, it loses less energy climbing out of shallow gravitational wells, which can slightly alter how we perceive its wavelength. Combined with the faster local expansion, this can make galaxies appear to recede at higher velocities than they actually are. Such effects accumulate over cosmological distances, influencing the inferred value of H0 derived from local observations. Some researchers have gone even further, proposing modified versions of cosmological models, like the Lemaitre-Tolman-Bondy (LTB) model, that explicitly account for spherical inhomogeneities in density, such as a central void. These models demonstrate that it's theoretically possible for an observer near the center of a massive underdensity to see a locally higher Hubble constant without violating the basic principles of general relativity. The key point is that what we perceive as the universe's expansion rate may depend on where we stand within its vast cosmic landscape. If this turns out to be true, the consequences for cosmology would be profound. It would mean that the apparent acceleration of the universe, and perhaps even some of our understanding of dark energy, could be influenced by our local cosmic geography. It wouldn't negate dark energy's existence, but it would remind us that the universe's expansion is not as cleanly uniform as our equations assume. In this light, the KBC Void hypothesis offers more than just a technical fix for the Hubble tension. It represents a shift in perspective, a humbling reminder that we're not detached observers of the cosmos, but participants embedded within its grand, uneven structure. The space around us isn't neutral. It shapes the data we collect, the conclusions we draw, and the very constants we use to describe reality. And as astronomers continue to refine their maps of the universe, new observations are providing tantalizing hints that our local region really is underdense. Surveys of galaxy distributions, redshift data, and large-scale structure mapping all point toward a local dip in density consistent with a void-like structure on the scale of the KBC Void. These findings don't prove the hypothesis yet, but they certainly keep it alive, suggesting that the emptiness around us might be more than coincidence. This brings us naturally to the next crucial piece of the story: observational evidence. What do we actually see when we look out into the universe, and how does that support, or challenge, the idea that we live inside a cosmic void? The answers lie in the intricate maps of galaxies and the subtle fingerprints of large-scale structure that astronomers have been piecing together for decades. Evidence for the KBC Void, or at least for some kind of underdense region surrounding us, doesn't come from speculation alone. It's grounded in decades of observational data collected from deep sky surveys, redshift measurements, and maps of galaxy distribution stretching across billions of light-years. These observations consistently hint at one striking feature of our cosmic neighborhood. The universe near us seems to contain fewer galaxies and less matter than expected if the cosmos were perfectly uniform on large scales. One of the earliest and most direct pieces of evidence came from galaxy counts. Astronomers conducting wide-field surveys, like the 2MASS 2-micron all-sky survey and the Sloan Digital Sky Survey SDSS, have spent years cataloguing the distribution of galaxies in every direction. When these data were compiled into three-dimensional maps, scientists noticed something peculiar. Within a radius of roughly 300 to 500 megaparsecs, about 1 to 2 billion light-years, the density of galaxies appears to be about 20% lower than the cosmic average. In other words, there's a noticeable dip in how many galaxies populate our local region of the universe. This isn't a small-scale feature like a local cluster or filament gap. It's a large, coherent underdensity that extends across enormous distances. The 2013 study by Keenan, Barger, and Cowie quantified this effect by analyzing near-infrared galaxy counts from the Euclid Infrared Deep Sky Survey and 2MASS. They found that the local universe, extending out to a redshift of around Z, approximately 0.07, appeared significantly underdense compared to more distant regions. Beyond that distance, galaxy density began to rise again, suggesting that our region sits within a broad, shallow cosmic depression, the very structure we now refer to as the KBC Void. Additional evidence has emerged from supernova observations, which serve as cosmic distance markers. When Type Ia supernovae are used to measure expansion rates in different parts of the sky, subtle variations emerge that correspond to differences in local density. In regions that appear to be underdense, supernovae seem slightly brighter than expected, a sign that space there is expanding faster. Several studies, including those led by cosmologists like Krzysztof Bolejko and Michael Hudson, have shown that the local expansion rate inferred from supernova data could indeed be elevated due to a large-scale underdensity. Galaxy velocity surveys have provided further clues. The Cosmic Flows Project, for instance, measures the peculiar velocities of galaxies, their motions relative to the overall Hubble flow of expansion. What researchers have found is that galaxies near our region show patterns consistent with being inside a large void. They're flowing outward toward denser regions, much like air rushing away from a low-pressure system. This bulk flow behavior matches what would be expected if the Milky Way resided in a giant, underdense bubble. Even the kinematic Sunyaev-Zeldovich effect, KSZ effect, which measures the motion of galaxy clusters through the cosmic microwave background, provides indirect support. Clusters on the edges of a void should exhibit characteristic velocity shifts as they move toward denser regions. Observations of the KSZ effect across large scales have revealed flow patterns that some scientists interpret as consistent with a local void structure, though the data are still being refined. One of the most persuasive arguments, however, comes from multi-wavelength analyses that combine optical, infrared, and radio data. By using multiple observational bands, astronomers can better correct for dust, extinction, and selection biases that might skew galaxy counts. When these corrections are applied, the underdensity remains, robust across different wavelengths and survey methods. That consistency strengthens the case that the observed dip in density is real, not an artifact of how we collect or process data. Moreover, this underdensity appears to extend well beyond our local galactic neighborhood. Structures like the local void, first identified in the 1980s, already hinted that our Milky Way, lies adjacent to a region with remarkably few galaxies. The KBC Void could simply be the much larger, encompassing structure that includes and extends beyond the local void, embedding it in a more extensive underdense region that stretches across much of our observable horizon. It's also worth noting that the underdensity isn't uniform in all directions. Surveys suggest some anisotropy, slight variations depending on where we look, which is expected in a complex cosmic web. These irregularities are natural. Voids are rarely perfect spheres. They tend to have irregular, filament-threaded shapes, with denser walls and sparser centers. From our position, this could mean that some parts of the sky appear richer in galaxies, while others appear more barren, depending on where the edges of the void lie. However, not all evidence points unambiguously toward the existence of a massive void. Some astronomers argue that the observed underdensity might be partly due to observational bias. For example, incompleteness in galaxy surveys, limited sky coverage, or uncertainties in distance measurements. Yet, as newer and more comprehensive surveys emerge, such as the Dark Energy Survey, DES, Euclid, and the upcoming Vera Rubin Observatory's LSST, these systematic uncertainties are shrinking. So far, the overall trend persists. On scales of about 1 to 2 billion light-years, our region of the universe still looks slightly emptier than average. If this underdensity is real, it doesn't just change our cosmic address. It influences how we interpret nearly every major cosmological measurement. The fact that galaxy counts, supernova brightness, and velocity flows all point to the same conclusion gives the void hypothesis a degree of coherence that's hard to dismiss. It ties together multiple lines of evidence across different observational methods, each reinforcing the idea that we inhabit a special kind of cosmic landscape, one where emptiness itself might be shaping our view of the cosmos. Still, science demands caution. Extraordinary claims require extraordinary proof, and while the data are compelling, they're not yet definitive. The next generation of surveys will help settle the question, mapping the three-dimensional structure of the nearby universe with unprecedented precision. If they confirm that we're truly sitting inside a 2 billion light-year wide underdense region, it would represent one of the most significant paradigm shifts in modern cosmology. But before we draw such sweeping conclusions, it's important to consider the alternatives. Could the Hubble tension and the observed underdensity be explained by something else? Perhaps new physics, exotic forms of dark energy, or subtle errors in our measurement techniques? The alternative explanations are just as fascinating, and exploring them helps us understand whether the void hypothesis is a necessary truth or just one possibility among many. While the void hypothesis offers a compelling and intuitive way to explain the Hubble tension, it's far from the only theory on the table. In fact, the discrepancy between local and cosmic measurements of the universe's expansion rate has become one of the most hotly debated puzzles in astrophysics precisely because there are so many plausible explanations, ranging from subtle observational errors to revolutionary new physics. The truth may lie in one of these alternatives, or perhaps in a combination of several. To understand why the void idea stands out, and where it may fall short, we have to explore these competing explanations in detail. Let's begin with the most conservative possibility: measurement errors and calibration issues. The Hubble constant isn't something astronomers can measure directly. It's inferred through complex, multi-step methods known as the cosmic distance ladder. This ladder relies on a chain of overlapping measurements, each introducing its own potential uncertainties. For nearby stars, distances are measured using parallax, the tiny shift in position as Earth orbits the Sun. These calibrate Cepheid variable stars, which are used to estimate distances to nearby galaxies. Those galaxies then host Type 1a supernovae, which serve as standard candles for measuring even farther galaxies. If there's even a small bias or systematic error in any of these rungs, say in how Cepheids are calibrated, how dust extinction is corrected, or how supernova brightness is standardized, it could easily skew the inferred value of the Hubble constant. For years, skeptics of the tension have argued that such systematics could explain the discrepancy. However, as instruments like the Hubble Space Telescope and Gaia have refined these calibrations, the local measurements have only grown more precise, and yet the tension persists. That persistence suggests the difference isn't just a measurement artifact. The next possibility is that the tension arises from new physics beyond the standard cosmological model. In the prevailing lambda cold dark matter model, the universe's expansion history is governed by three main ingredients: ordinary matter, dark matter, and dark energy, represented by the cosmological constant, L. If the Hubble tension is real, it could mean that one or more of these components behaves differently than we currently assume. For instance, some cosmologists propose early dark energy, EDE, a form of dark energy that was more influential in the early universe, just before the formation of the cosmic microwave background. If dark energy briefly flared up, then faded away, it could have altered how quickly the universe expanded in its youth, thereby changing the relationship between early and late expansion rates. Models of early dark energy can, in some cases, bring the CMB inferred Hubble constant into closer alignment with local measurements, though these models often require fine-tuning and can create new inconsistencies elsewhere. Another intriguing possibility involves modifications to the properties of dark matter. The standard model assumes that dark matter is cold, meaning its particles move slowly and interact only through gravity. But if dark matter were instead warm or self-interacting, it could influence how structures formed in the early universe, subtly changing the inferred expansion rate derived from the CMB. Similarly, the introduction of extra-relativistic particles, sometimes described as dark radiation or additional neutrino species, could alter the early expansion rate enough to help reconcile the two measurements. Then there are proposals that question the very nature of gravity itself. In modified gravity theories, such as those extending Einstein's general relativity, the strength of gravity or its relation to space-time curvature might vary slightly over cosmic time. This could affect how both matter and light respond to expansion. Models like F of R gravity or scalar tensor theories have been explored as ways to tweak cosmic expansion without requiring exotic forms of dark energy. But they remain speculative and face constraints from other observations, such as gravitational lensing and the CMB power spectrum. Still, other ideas involve inhomogeneous cosmology, which, unlike the void hypothesis, doesn't necessarily place us in a specific location within a structure like the KBC Void, but instead considers that the universe's large-scale distribution of matter might not average out as smoothly as we think. In these models, variations in density across vast regions could mimic some of the effects attributed to dark energy or alter how we perceive cosmic expansion. The void hypothesis is essentially a specific and extreme case of this broader approach, one in which our location happens to lie within a massive underdensity. Yet, not all explanations rely on invoking exotic physics or environmental effects. Some cosmologists point to potential statistical anomalies in how the data are analyzed. For example, if galaxy surveys are not fully representative of the cosmic average, perhaps due to incomplete sky coverage or cosmic variance, random fluctuations in density, then our inferred values of the Hubble constant could be slightly biased. Similarly, the models used to extract H0 from the CMB depend on a set of assumptions about the universe's composition and geometry. If any of those assumptions, such as the flatness of space or the exact nature of dark energy, are slightly off, It could lead to systematic differences between early and late universe measurements. Among all these possibilities, the void hypothesis occupies a unique middle ground. It doesn't require rewriting fundamental physics, but it also doesn't dismiss the tension as mere error. Instead, it offers an elegant environmental explanation grounded in the structure of the universe itself. It says, in essence, perhaps the data are correct, but our perspective isn't average. In this view, both the local and cosmic measurements of the Hubble constant could be right, just for different regions of the universe. From inside a vast underdense bubble, we would naturally observe a slightly faster expansion than an observer far beyond it. However, this solution comes with its own challenges. For the void hypothesis to fully account for the observed discrepancy, the underdensity must be very large and quite deep, larger than what standard cosmological simulations predict as likely to form from random fluctuations in the early universe. Observations so far support an underdensity, but not necessarily one deep enough to solve the tension on its own. Thus, many cosmologists suspect that the truth might be a combination of factors: a modest void contributing a local bias, combined with subtle new physics or still unrecognized systematic effects. The debate remains vibrant because the Hubble tension touches the foundations of cosmology. It's not merely about a number, it's about the coherence of the entire cosmic model. If we can't reconcile how the universe expands now with how it expanded in its infancy, something in our understanding is incomplete. Whether that missing piece is a vast cosmic void, a burst of early dark energy, or a flaw in our assumptions about gravity itself, solving the Hubble tension will reshape how we see the cosmos and our place within it. But before we can test any of these explanations, we need to understand a crucial constraint: scale. For the void hypothesis to truly solve the Hubble tension, the KBC void would need to be extraordinarily large and deep, perhaps larger than current models of structure formation allow. And that brings us to one of the most significant challenges facing this idea: the scale problem. The scale problem lies at the very heart of the debate over the KBC void, and it's the main reason many cosmologists hesitate to embrace the idea that our local underdensity could be responsible for the Hubble tension. While the notion that we live in a vast, low-density bubble offers an elegant and observationally grounded explanation for some of the discrepancies in cosmological measurements, the numbers behind it quickly push against the limits of what standard models of the universe say is possible. For the KBC void to fully account for the observed difference in expansion rates, it would need to be astonishingly large and remarkably deep, far beyond what current theories predict can naturally form through cosmic evolution. To understand why this is such a sticking point, we need to remember how structure forms in the universe. In the standard lambda-CDM cosmological model, the lambda cold dark matter framework that underpins modern cosmology, the universe began as a nearly uniform sea of matter and energy, sprinkled with minute density fluctuations. Over billions of years, gravity amplified these tiny differences, pulling matter together into clusters and filaments while leaving empty pockets, voids, in between. This process, known as hierarchical structure formation, is well understood and beautifully simulated by computer models. These simulations tell us something important. While cosmic voids are common, they typically range from tens to a few 100 million light-years across. Larger voids do exist. Supervoids, like the Boötes void, which spans about 330 million light-years, or the Eridanus supervoid, estimated at around 900 million light-years. But the proposed KBC void is on a completely different scale. At roughly 2 billion light-years across, it would be an order of magnitude larger than even the biggest known voids, a true cosmic anomaly. And it's not just the size that's problematic, it's the depth of the void. the degree to which it's underdense. Keenan, Barger, and Cowie's 2013 analysis suggested that the local matter density within this region is about 20 to 30% lower than the cosmic average. That might not sound like much, but on such a massive scale, it's a staggering amount of missing matter. To create a void of this magnitude and depth through the normal processes of gravitational clustering would require an exceptionally unlikely sequence of fluctuations in the early universe, essentially a 1 in a billion statistical anomaly. This is where cosmological models start to strain. Simulations based on lambda. Cold dark matter simply don't produce voids this vast and deep under normal conditions. The distribution of density fluctuations in the early universe, as observed in the cosmic microwave background, CMB, was extremely smooth, with variations on the order of 1 part in 100,000. Those tiny ripples grew over time to form the structures we see today, but not enough to create a billion light-year wide void with such a pronounced underdensity. To produce a KBC-sized void, the initial fluctuations would have had to be far larger, or the laws governing structure formation somewhat different than we currently believe. This creates a paradox. On one hand, observational data from galaxy counts, supernova brightness, and velocity flows suggest that our local region may indeed be underdense. On the other hand, the existence of such a huge and deep void appears highly improbable under the physics that we know. So, we're faced with two possibilities. Either the void is smaller or shallower than early estimates indicate, and therefore explains only part of the Hubble tension. Or our cosmological models are missing something fundamental about how large-scale structures form. Some researchers argue that we may be overestimating the void's scale because of limitations in the data. Galaxy surveys, while vast, still rely on incomplete coverage and indirect measures of distance. Cosmic variance, the statistical randomness inherent in where we happen to observe, can also make our region appear more unusual than it really is. In other words, maybe we're not sitting in the middle of a single, enormous void, but rather in a region that's part of a larger network of smaller, overlapping voids, collectively creating the illusion of a single supervoid. This patchwork could produce a similar observational effect, slightly boosting the local expansion rate, without requiring a structure as extreme as the original KBC model. Others take the opposite approach and suggest that perhaps the universe can produce such vast voids under the right conditions. If, for example, dark energy or dark matter behaves differently than we assume. If dark energy isn't perfectly constant throughout space, but instead slightly varies in strength, it could naturally create regions that expand faster than others, deepening voids over cosmic time. Alternatively, if dark matter has interactions beyond gravity, say, if it can dissipate energy or self-interact, it might clump less efficiently, allowing larger voids to persist and grow. Another possibility involves cosmic inflation, the brief but violent burst of expansion that occurred fractions of a second after the Big Bang. During inflation, quantum fluctuations were stretched to cosmic scales, seeding the density variations that would later form galaxies and voids. If inflation produced slightly stronger fluctuations in one region, that area could have evolved into a large, underdense bubble, possibly giving rise to something like the KBC Void. But this would require very fine-tuned initial conditions, and current inflation models don't naturally predict voids of such magnitude. The scale problem also touches on philosophical questions about the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales. This principle is deeply embedded in the foundations of cosmology, simplifying Einstein's equations and making the universe mathematically manageable. Yet, if the KBC void is real, it would suggest that our cosmic neighborhood is not representative of the universe at large. We would occupy a rare, atypical location, something that cosmologists have long resisted since it seems to reintroduce a kind of specialness to humanity's position in the cosmos. It's not that we'd be physically central to the universe, but we would be in an unusual spot, near the middle of a colossal underdensity that subtly warps our view of the cosmos. That specialness is precisely what makes the void hypothesis both intriguing and unsettling. The odds of finding ourselves in such a massive underdense region, purely by chance, seem slim. Yet the more data we collect, the more it appears that our part of the universe might indeed be atypical in some way. Whether that atypicality is enough to fully explain the Hubble tension remains uncertain, but even a partial contribution would be important. It would mean that local environmental effects cannot be ignored in precision cosmology. To truly determine whether the KBC Void is real, and if so, how big and deep it really is, cosmologists are turning to increasingly sophisticated tools. Simulations and high-resolution models are being used to test whether structures of this scale could form naturally, or whether their existence would require new physics. These simulations allow scientists to experiment with different parameters, changing the amount of dark matter, the behavior of dark energy, or the initial conditions of the universe, to see what kind of cosmic landscapes emerge. Thus, the scale problem isn't just a numerical challenge, it's a fork in the road for cosmology itself. Either our universe occasionally spawns gargantuan voids far larger than we once thought possible, or our theories of structure formation are incomplete. In either case, exploring this question brings us closer to understanding the true shape, texture, and dynamics of the cosmos, and perhaps even reshaping the principles that have guided cosmology for nearly a century. The next step in this journey involves turning from theoretical estimates to computational reality, seeing whether our simulations and models of the universe can reproduce something like the KBC Void, or whether they point us toward a deeper, as yet unknown truth about cosmic evolution. To test whether a structure as vast and underdense as the KBC Void could actually form under the laws of known physics, cosmologists have turned to one of the most powerful tools in their arsenal: numerical simulations of the universe. These simulations, intricate, multi-dimensional digital reconstructions of cosmic evolution, allow scientists to rewind the clock to the early universe and watch how matter and energy evolve over billions of years. By feeding the equations of general relativity and the lambda cold dark matter model into supercomputers, researchers can generate a virtual cosmos, seeded with the same tiny fluctuations in density that were imprinted in the cosmic microwave background after the Big Bang. From there, they can track how galaxies form, clusters grow, and, crucially, how voids emerge. What these simulations consistently reveal is that cosmic voids are a natural and inevitable feature of structure formation. They arise as dense regions. The filaments and clusters of the cosmic web pull matter inward, leaving behind expanding pockets of emptiness. Over time, these voids stretch and merge, growing larger as they push against surrounding filaments. Yet, in nearly every standard simulation based on lambda cold dark matter physics, voids tend to max out at a few 100 million light-years across. Even the largest supervoids formed in such models rarely exceed 1 billion light-years in diameter. That's impressive on a human scale, but still far short of the 2 billion light-year expanse attributed to the KBC Void. To investigate whether the KBC Void could arise naturally, researchers have adjusted parameters in these simulations, altering the distribution of dark matter, varying the initial conditions of density fluctuations, or changing the assumed properties of dark energy. Some of the most detailed efforts come from teams using simulations like Illustris, Millennium, Eagle, and Bolshoi-Planck, which trace the growth of billions of galaxies over cosmic time. These models incorporate not only gravity, but also the effects of gas dynamics, radiation, star formation, and feedback from black holes, all of which influence how structures evolve. The results so far suggest that while large voids can form, reproducing something of the scale and depth of the KBC void under standard physics is extremely rare, perhaps a 1 in a million statistical fluke. In other words, the formation of such a structure is not strictly impossible, but it would be an exceptional event in a universe governed by lambda-cold dark matter. For it to occur, the initial density fluctuations in that region would have to be unusually low, creating a primordial underdensity that expanded faster than its surroundings right from the universe's infancy. This kind of supervoid seed would evolve over billions of years into the vast emptiness we might inhabit today. To see whether this could have happened, cosmologists run ensembles of simulations, hundreds or even thousands of different universes, each starting with slightly different random seeds for the initial density field. These virtual universes evolve independently, allowing scientists to study the range of possible outcomes. By analyzing the largest voids that form in these simulations, researchers can estimate how probable it is for something like the KBC Void to exist. The consensus so far: the odds are small, but non-zero. Some simulation runs do produce vast underdensities approaching 1 billion light-years in diameter, though these tend to be shallower than the KBC Void's proposed 20 to 30% density deficit. What's particularly interesting is that the shape and environment of these simulated voids often resemble what we observe around the Milky Way. The simulated galaxies inside these voids tend to be smaller, less clustered, and exhibit faster local expansion rates, mirroring the kinds of observational features we actually see. This suggests that even if our local underdensity isn't as deep or extreme as initially proposed, the general idea of living within a large, gently expanding void is consistent with the structure formation process. However, the question remains: could such a void really reach the colossal scale suggested by the KBC model? Some cosmologists have proposed that modifying dark energy or dark matter physics could make it more plausible. For instance, if dark energy isn't perfectly uniform, if its density or pressure varies slightly across space, it could amplify the expansion of underdense regions, effectively deepening and widening voids over cosmic time. Likewise, if dark matter interacts weakly with itself, a scenario known as self-interacting dark matter, it could slow down the collapse of dense regions, allowing voids to dominate larger volumes. These ideas remain speculative, but they're being explored through custom simulations designed to test how alternative physics might shape the large-scale structure of the cosmos. Another line of investigation focuses on non-linear effects in cosmic evolution. Most early simulations treated large-scale structure formation as a relatively smooth process, where the average density fluctuations grew in a predictable Gaussian manner. But as computational power increased, cosmologists realized that voids and filaments interact in more complex, non-linear ways. When multiple voids merge, a process known as void percolation, they can form enormous composite structures that behave like single, supersized voids. In some high-resolution simulations, these megavoid complexes stretch across distances comparable to the KBC void, though their density contrasts are typically milder. It's possible that our local universe is part of such a percolated network of merged voids, rather than a single massive depression, a subtle but crucial distinction that might reconcile observations with theory. Researchers have also used cosmological reconstruction techniques, which work backward from observed galaxy distributions to infer what the early density field must have looked like. These reconstructions, based on Bayesian statistical frameworks, allow scientists to test whether the KBC void could have plausibly evolved from realistic initial conditions. Preliminary findings indicate that, while such an underdensity could in principle grow naturally, it would require starting conditions that are on the extreme tail of what's statistically likely given the CMB's observed smoothness. All of this highlights a delicate tension between observation and theory. Observations suggest that our local region may indeed be underdense, while simulations indicate that such vast voids should be rare, but not impossible. That gap between improbable and impossible keeps the KBC hypothesis alive. Cosmologists know that the universe has surprised them before, with dark energy, with accelerated expansion, with black holes forming earlier than expected. It wouldn't be the first time that nature has turned out to be more extreme than our models allow. The ongoing work in simulations is also helping refine our expectations for what signatures such a void should produce in observable data. For instance, in the temperature fluctuations of the cosmic microwave background, or in the way light from distant galaxies bends and stretches as it passes through large-scale structures, a phenomenon known as gravitational lensing. These predicted signatures offer a way to test the KBC hypothesis directly against reality. If we truly live inside a supervoid, it should leave faint but measurable imprints on the CMB and on the distribution of galaxies beyond its edge. That leads us naturally to the next crucial question. How do we compare this hypothesis to the ultimate benchmark of cosmic uniformity, the cosmic microwave background itself? The CMB is the oldest light in the universe, a near-perfect map of its density fluctuations at the dawn of time. Any model proposing that we live in a vast, underdense region must be consistent with the remarkable uniformity of that ancient light. So, can the void hypothesis pass that test? That's what we'll explore next. The cosmic microwave background, CMB, is the universe's oldest and most pristine messenger, a faint bath of radiation left over from the Big Bang, released about 380,000 years after the universe began. Long before stars, galaxies, or even voids existed, the cosmos was a dense, hot plasma of particles and light. When the universe cooled enough for atoms to form, photons could finally travel freely. And those ancient photons have been streaming through space ever since. Today, they reach us as a near-uniform glow across the sky, with a temperature of roughly 2.725 Kelvin. This light, first detected accidentally in 1965 by Arno Penzias and Robert Wilson, is often called the afterglow of creation. It's more than just a relic. It's a snapshot of the early universe, a cosmic photograph frozen in time. Embedded within it are faint fluctuations, variations in temperature of only a few millionths of a degree, which correspond to the tiny density differences that later grew into galaxies, clusters, and voids. Because the CMB captures the universe at such an early, unpolluted stage, it provides an independent check on the uniformity of the cosmos. That's what makes the CMB such a crucial test for the void hypothesis. If we truly live inside a massive underdense region, like the proposed KBC Void, that structure must be consistent with the near-perfect isotropy, uniformity in all directions, observed in the CMB. In other words, the existence of such a huge void shouldn't contradict the CMB's smoothness or the large-scale patterns imprinted on it. At first glance, this seems problematic. A void spanning 2 billion light-years sounds like it should leave a massive imprint on the CMB. After all, such a region would slightly alter the gravitational potential of space. And since photons traveling through regions of differing density are affected by those gravitational fields, we'd expect to see corresponding temperature shifts in the CMB. Specifically, photons entering an underdense region lose energy climbing in, then gain less energy climbing out, because the void's gravitational potential decays over time. This creates a subtle temperature dip in the CMB known as the Integrated Sachs-Wolf (ISW) effect. If the KBC void exists, and we're near its center, its gravitational imprint should appear as a faint but measurable cold spot in the CMB, a region slightly cooler than its surroundings. Interestingly, there is a well-known anomaly in the CMB called the cold spot, first identified in data from the WMAP satellite and later confirmed by Planck. This feature covers a patch of sky about 10 degrees across and is noticeably cooler than the surrounding regions by about 70 microkelvin. Some scientists have proposed that it could be the signature of a large cosmic void, perhaps one not unlike the KBC void, lying along our line of sight. However, the relationship between the KBC void and the CMB cold spot remains uncertain. The cold spot is located in the direction of the constellation Eridanus and appears to correspond to a real underdensity, the Eridanus supervoid, detected in galaxy surveys. But the KBC void, as proposed, is far larger and more encompassing, potentially extending in all directions rather than being localized. If we're inside such a void, its effects would be more subtle and diffuse, influencing the overall pattern of the CMB rather than creating a distinct patch. To test this, cosmologists use relativistic ray tracing simulations to model how CMB photons would be affected if they passed through a void the size and depth of the KBC. These simulations incorporate general relativity to track how the gravitational potential of the void evolves over time, and how that evolution distorts the energy of photons. The results show that a void with a moderate underdensity, say 20 to 30% below average, could produce small but detectable ISW signals consistent with current CMB data, without violating isotropy. However, a void deep enough to fully explain the Hubble tension might leave imprints too strong to reconcile with the observed smoothness of the CMB. This is the balancing act that the void hypothesis faces. On one hand, it needs to be large and deep enough to affect local expansion rates and produce a measurable bias in the Hubble constant. On the other, it must be shallow enough not to disrupt the exquisitely uniform CMB we observe. Too deep a void, and it would generate ISW, or gravitational lensing effects, that would show up as glaring anomalies in the Planck data, which, so far, we simply don't see. That said, the CMB does exhibit subtle hemispherical asymmetries, small differences in average temperature fluctuations between opposite sides of the sky, that have long puzzled scientists. Some researchers have speculated that these asymmetries could hint at large-scale inhomogeneities in matter distribution, potentially consistent with living inside an extended underdense region. Yet these correlations remain weak and controversial. Most cosmologists caution against overinterpreting them, noting that random statistical noise can mimic such asymmetries. A more direct way to test the void hypothesis with the CMB involves gravitational lensing, the bending of light by large-scale structures. Dense regions, like galaxy clusters, magnify and distort the CMB behind them, while voids do the opposite, slightly demagnifying the background radiation. By measuring the CMB's lensing potential map, essentially a blueprint of how light has been deflected on its way to us, scientists can infer the large-scale distribution of matter. If we lived inside a huge void, that lensing pattern should show a distinct, large-scale deficit in projected mass around our location. So far, the Planck lensing maps haven't revealed any evidence for such a giant void centered on the Milky Way. The data remain consistent with the standard cosmological principle that, on scales larger than a few 100 million light-years, the universe is statistically uniform. This doesn't completely rule out the KBC void, but it suggests that if it exists, it must be shallower or more complex than a single spherical underdensity. Perhaps instead, our local region is part of a network of overlapping voids, gradually transitioning into denser surroundings, a cosmic basin rather than a distinct bubble. Ultimately, the CMB provides both a constraint and a compass for the void hypothesis. Any model proposing that we inhabit a vast underdensity must fit neatly within the limits of what the CMB allows, preserving its near-perfect isotropy while subtly influencing local expansion. Achieving that balance is difficult, but not impossible. In fact, some cosmologists argue that the KBC void could represent a gentle, large-scale gradient in density rather than a sharply bounded cavity, enough to influence local measurements without leaving a strong CMB signature. As powerful as the CMB is, however, it's not the only large-scale structure test available. To truly understand how the KBC void fits within the cosmic landscape, we have to compare it to other known structures, the filaments, clusters, and superclusters that define the cosmic web. And at the center of that web lies our own galactic home, the Laniakea supercluster. Examining how the KBC void relates to Laniakea and its neighboring structures offers a fascinating glimpse into how our region fits within the broader geometry of the universe. The KBC void doesn't exist in isolation. It's part of a much larger cosmic landscape, one woven together by gravity into an intricate cosmic web of filaments, clusters, and empty spaces. To understand where our hypothesized void fits in, we first have to look at our local cosmic neighborhood, the Laniakea supercluster. Discovered in 2014 by Brent Tully and colleagues, Laniakea is an enormous gravitationally bound region encompassing about 100,000 galaxies spread across 520 million light-years. The Milky Way, along with the Virgo cluster and thousands of other galaxies, resides within it. The name Laniakea means immense heaven in Hawaiian, a fitting title for a structure so vast it defies easy comprehension. What's fascinating is that Laniakea itself sits near the center of a broader network of filaments and voids, acting like an island in an ocean of emptiness. Within this cosmic web, galaxies are not distributed evenly, but arranged in strands of matter, colossal filaments connected like neural pathways. Between these filaments are vast regions of near-nothingness, cosmic voids. The KBC void, according to current models, could be the massive underdense region surrounding and enclosing parts of Laniakea, stretching well beyond its boundaries. In this sense, our supercluster might be the dense ridge near the bottom of a gently sloping cosmic basin. This layered structure, filaments bordered by emptiness, is typical of how the universe organizes itself on the largest scales. Matter flows along filaments into gravitational wells, while the spaces between them gradually expand, deepening voids over billions of years. If the KBC void exists, it's not an anomaly, but a particularly large and diffuse example of this pattern, a region where the local filament network, including Laniakea, is surrounded by more sparsely populated cosmic territory. What makes this configuration especially interesting is that it helps contextualize why our measurements of cosmic expansion might differ from those made elsewhere. If the Milky Way lies near the center of a supercluster that itself sits inside a vast underdensity, our vantage point is doubly influenced by both the local gravitational pull of Laniakea and the accelerated expansion of the surrounding void. Together, these effects could subtly warp the way we measure distances, redshifts, and the Hubble constant. In short, the KBC void fits into a grand hierarchy. Galaxies form clusters, clusters form superclusters, and between them stretch enormous, faintly glowing corridors of matter, all embedded in a sea of emptiness. Our home in the Laniakea supercluster may be more special than we ever imagined. Perched at the edge of an immense gravitational structure and at the center of one of the universe's largest empty domains. Next, we'll explore what this could mean for cosmology as a whole, because if the void hypothesis holds true, it doesn't just reshape our local map of the universe. It challenges one of cosmology's most sacred assumptions, that the universe, on large scales, is the same everywhere. If the KBC Void is confirmed to exist at the scale and depth proposed, it would represent far more than a new entry in the cosmic atlas. It would shake the foundations of modern cosmology itself. That's because it directly challenges one of the discipline's most essential assumptions, the cosmological principle. This principle, elegant, simple, and powerful, holds that on large enough scales, the universe is both homogeneous, the same everywhere, and isotropic, the same in every direction. It's the philosophical cornerstone of the lambda cold dark matter model, the framework that describes the universe's evolution from the Big Bang to today. For over a century, this idea has guided cosmologists in building models of cosmic expansion, dark energy, and structure formation. It allows Einstein's equations to be simplified into a form that predicts a smoothly expanding universe, rather than one that varies chaotically from place to place. But if we truly live inside a vast underdense region, a 2 billion light-year wide cosmic depression, then the universe, from our vantage point, isn't as uniform as we've assumed. In that case, the cosmological principle might hold globally, but not locally. That distinction is crucial. Cosmologists have long known that on small scales, among galaxies, clusters, and filaments, the universe is far from homogeneous. But the principle was thought to kick in at scales above about 300 million light-years, where all local irregularities would statistically even out. The KBC Void, however, operates at scales several times larger than that. If our cosmic neighborhood truly deviates from the universal average over such distances, it means that our location is atypical, even if the universe as a whole remains statistically uniform. This possibility raises deep questions. If our position inside an underdensity affects how we measure cosmic expansion, then many of our most trusted cosmological parameters, from the Hubble constant to the density of dark energy, might be context-dependent rather than absolute. It would mean that observers in different regions of the universe could measure slightly different versions of the cosmos, depending on their local environment. The universe might not appear identical everywhere, not because physics changes, but because perspective does. Such an idea isn't entirely new. In fact, models that relax the cosmological principle have existed for decades, notably the Lemaitre-Tolman-Bondi (LTB) models. These describe universes that are spherically symmetric but inhomogeneous, allowing density, and therefore expansion, to vary with radius. In these frameworks, an observer inside a large underdense bubble would see an apparently accelerated expansion, even if dark energy didn't exist at all. Though the KBC Void doesn't eliminate the need for dark energy, it echoes this concept that where we are can mimic or modify cosmic phenomena we attribute to universal laws. If verified, the implications would ripple through nearly every aspect of cosmology. For example, Hubble's constant might not be constant. Instead, it could vary slightly depending on local matter density. That would mean our Hubble tension isn't a crisis in physics, but a reflection of environmental bias. The cosmic age could differ slightly when measured locally versus globally, since a faster local expansion implies a slightly younger inferred universe from our viewpoint. Dark energy's influence might appear stronger to us because we're in an underdense region that expands more rapidly than average, exaggerating the apparent acceleration of the universe. On a deeper level, confirming the KBC Void would also carry a philosophical weight. It would suggest that, despite centuries of scientific effort to remove humanity from any special place in the cosmos, from the Earth-centered universe to the Sun-centered solar system to the galaxy among billions, we may occupy an unusual region after all. Not the literal center of the universe, but perhaps the quiet center of a vast emptiness. Cosmologists would need to revisit the assumption that averaging over sufficiently large volumes always smooths out irregularities. If the universe's structure remains clumpy, even on billion light-year scales, it could mean that large-scale inhomogeneities are more important to cosmic evolution than we've realized. This might lead to revisions in how we model dark matter distribution, cosmic flows, and the geometry of space-time itself. Ultimately, confirming that we live inside a massive cosmic void would be a profound reminder that the universe's beauty lies in its complexity, that its symmetry is not perfect, and that our understanding of it is always a work in progress. The cosmological principle wouldn't necessarily be wrong, but it would be redefined, not as an absolute truth, but as an approximation that fails in exceptional places. And we might just live in one of those places. Yet beyond the scientific implications, there's also something deeply human about this realization, something that touches our sense of perspective and place. And that's where the discussion naturally turns next, to the philosophical implications of living in a universe where our cosmic home might be not in the heart of brilliance, but in the heart of emptiness. If the KBC Void truly exists, then its discovery is not just a scientific revelation, it's a deeply philosophical one. It invites us to rethink not only where we are in the cosmos, but what that means. For centuries, humanity has wrestled with its place in the universe, moving step by step away from the comforting illusion of centrality. First, Earth lost its throne when Copernicus showed that we revolve around the Sun. Then, the Milky Way was revealed to be just one of countless galaxies. And now, perhaps, we find ourselves in a position even more humbling, at the center of a vast, silent cosmic void, an enormous expanse of almost nothing. There is something profoundly poetic about that. We are creatures of matter, consciousness born from stardust, living on a small planet orbiting an average star, nestled inside a galaxy adrift in an underpopulated patch of the universe. If the void hypothesis holds true, then our cosmic address is not in a bustling metropolis of galaxies, but in a cosmic desert, a lonely region where the nearest clusters and filaments are farther away, where the night sky might be, on average, less crowded than it could have been in other corners of the cosmos. This revelation challenges not only scientific principles, but also our psychological relationship with the universe. It underscores a recurring theme in the story of human discovery. Each time we think we've found our place, the universe shows us how small and rare that place truly is. And yet, instead of diminishing us, this truth adds depth to our existence. To live in a cosmic void is to live in the quiet space between galaxies, a vantage point of extraordinary isolation and clarity, where the universe's grand structure unfolds all around us, distant and magnificent. There's also an unsettling beauty in the idea that we're surrounded by emptiness. The vastness of the KBC Void reminds us that most of the universe is not filled with galaxies or stars, but with nothingness, dark, silent, and cold. And yet, within that emptiness, life emerged. Intelligence arose. Consciousness developed the capacity to look out into the void and wonder what it all means. The very fact that we can contemplate our place in this immense vacuum gives that emptiness meaning. In a way, living in a cosmic void reflects the human condition itself. We are small beings, suspended between immense forces, surrounded by silence, searching for meaning in the spaces between the stars. The void is both literal and metaphorical, the dark space outside and the existential space within. Perhaps that's why the idea resonates so strongly. It mirrors our deepest questions about isolation, connection, and purpose in a universe that seems indifferent to our existence. But this perspective is not one of despair, it's one of wonder. The realization that we inhabit an unusually empty region doesn't make us insignificant. It makes our presence all the more extraordinary. Against impossible odds, in one of the quietest neighborhoods of an unimaginably vast cosmos, life found a way. We are the lone observers in a region where almost nothing happens. Yet we are capable of understanding the very structure of the universe that shaped our isolation. So, when we gaze at the night sky, perhaps we should see the darkness differently. The faint glimmers of distant galaxies are not just stars scattered in the void. They are reminders that even in the universe's most barren expanses, there is connection, there is light, and there is meaning to be found. Living inside a cosmic void, then, is not a curse of loneliness. It is an opportunity for perspective. It shows us that our place in the cosmos is both ordinary and extraordinary. Ordinary in its physical nature, but extraordinary in its capacity for awareness. We are the void's consciousness, the part of emptiness that has learned to question itself. And while these reflections may sound poetic, they carry real scientific weight. Understanding our position within the cosmic web doesn't just change how we feel about the universe, it changes how we measure and interpret it. But as we'll see next, those measurements are far from easy. Determining whether we truly live in such a vast, underdense region pushes the limits of astronomy itself, and the challenges of doing so are as immense as the void we're trying to understand. Measuring the true structure and density of the universe, especially something as immense and diffuse as the KBC Void, is one of the most technically challenging tasks in all of astronomy. The concept itself sounds simple. Count galaxies, measure how far away they are, and determine how their distribution changes with distance. But in practice, mapping the large-scale density of the cosmos is a delicate, multi-layered process that pushes the boundaries of observation, computation, and even statistical inference. To confirm or refute the existence of a supervoid billions of light-years wide, astronomers must grapple with the inherent difficulty of observing structures that unfold across cosmic time itself. At the core of this challenge is the fact that we can't see the universe in real time. When we observe distant galaxies, we're looking back in time, sometimes billions of years into the past. That means every map of the cosmos is also a time-lapse, showing not just space, but evolution. The farther out we look, the younger the universe was. So when scientists try to measure the distribution of galaxies across billions of light-years, they must account for how the universe's structure, density, and expansion have changed over those eons. It's like trying to chart the topography of a mountain range while watching it slowly erode. The first and most fundamental tool in this work is the Redshift survey. Every galaxy emits light, and as the universe expands, that light stretches, shifting toward the red end of the spectrum. The greater the redshift, the farther away and older the galaxy is. By measuring the redshifts of millions of galaxies, astronomers can build a three-dimensional map of the universe, where each data point represents not just a location, but also a moment in cosmic history. Large-scale surveys, such as the Sloan Digital Sky Survey, SDSS, 2MASS, and the Dark Energy Survey, DES, have created vast catalogues of these redshifts, giving us our best look yet at how matter is distributed on cosmic scales. But even these incredible datasets have limitations. For one, galaxy surveys are incomplete, especially at great distances. Beyond certain magnitudes, galaxies become too faint for even the most sensitive telescopes to detect. Dust within our own Milky Way can obscure large portions of the sky, creating what astronomers call the zone of avoidance, an observational blind spot near the galactic plane where the density of stars and dust makes it nearly impossible to see beyond. This means that even our best maps of the universe have missing data, enormous gaps that must be statistically reconstructed. To estimate cosmic density, scientists use not just counts of galaxies, but models that weigh their luminosity, mass, and clustering behavior. Brighter, more massive galaxies tend to live in denser regions, while smaller, dimmer ones are more common in voids. By combining brightness data with redshift information, cosmologists can estimate the matter density contrast, essentially how much more or less matter a region contains compared to the cosmic average. The key variable, denoted delta, measures this difference. A delta of 0 means the region matches the average cosmic density, while negative delta values indicate underdensities, the signature of voids. For the KBC Void, researchers rely heavily on infrared surveys, such as those conducted by two MASS and the UKIRT Infrared Deep Sky Survey. Infrared light penetrates dust better than visible light, allowing astronomers to see deeper into obscured regions of space. Using these datasets, Keenan, Barger and Cowie in 2013 found that within a radius of about 300 megaparsecs, nearly 1 billion light-years, the density of luminous matter appeared to be about 20 to 30% lower than the cosmic mean. Beyond that distance, galaxy density rose again, suggesting we're embedded in a vast, shallow depression, precisely the kind of feature expected of a supervoid. However, confirming such an underdensity requires exquisite precision, and therein lies another difficulty. Small errors in distance measurement can mimic the appearance of a void. Because galaxies are constantly moving, their apparent redshifts include not just the effect of cosmic expansion, but also local peculiar velocities, motions caused by gravitational interactions with nearby clusters and filaments. These velocity components can distort the apparent positions of galaxies in redshift space, creating what are known as redshift space distortions. To correct for them, cosmologists must model the motions of galaxies on vast scales, a task that requires both accurate data and sophisticated simulations. There's also the problem of cosmic variance, the fact that every observer occupies a unique location in the universe and therefore sees a slightly different cosmic landscape. No matter how large a survey becomes, it can only map the universe from one vantage point. That means our estimate of the average density might be biased by our particular position. Ironically, the very phenomenon the KBC Void hypothesis is trying to explain. This statistical uncertainty makes it extremely difficult to determine whether a large underdensity is a universal feature or simply a local coincidence. To overcome these limitations, astronomers combine multiple independent measurements, not just galaxy counts, but also observations of supernovae, gravitational lensing, and the cosmic microwave background, CMB. For instance, regions with lower matter density should exhibit weaker gravitational lensing, less bending of light from distant sources. By comparing observed lensing signals to predicted ones, scientists can estimate the total mass distribution, including both visible and dark matter. Similarly, supernova brightness can serve as a check on expansion rate variations. Supernovae in underdense regions appear slightly brighter because space expands faster there, bringing them closer than expected for their redshift. These cross-checks help confirm whether apparent voids are real physical structures or statistical artifacts. Even with all this data, constructing a reliable three-dimensional map of the universe is computationally monumental. It requires combining billions of data points, correcting for observational biases, and reconstructing the density field using complex algorithms. Modern cosmologists employ Bayesian inference and machine learning models to fill in gaps, simulate missing regions, and statistically infer the most likely structure of space. These tools can even reverse engineer the universe, tracing its observed structure backward in time to reconstruct what the early density field must have looked like. The scale of these efforts is staggering. Projects like the Dark Energy Spectroscopic Instrument, DESY, are measuring redshifts for tens of millions of galaxies and quasars across a third of the sky, while future missions like Euclid and the Vera Rubin Observatory's Legacy Survey of Space and Time, LSST, will map billions of galaxies with unprecedented precision. These surveys will provide a direct test of the KBC hypothesis. If our local region is truly underdense, it should appear as a clear gradient in galaxy density extending across hundreds of millions of light-years. If, instead, the data reveal a smoother transition, then our cosmic environment might be closer to average than the current models suggest. The challenge, then, isn't just technical, it's conceptual. Measuring the large-scale structure of the universe requires grappling with our position within it. Every observation we make is filtered through the geometry of space, the distortion of time, and the biases of perspective. It's a reminder that cosmology is, in many ways, a study of shadows, trying to reconstruct the true shape of an unseen world from the faint light that reaches us across eons. Still, we stand at a turning point. The next generation of deep sky surveys and space missions will soon deliver data of such fidelity that we'll be able to test the KBC Void hypothesis directly, not through inference, but through observation. If they confirm that we inhabit a massive underdensity, it will not only solve part of the Hubble tension, but also reshape how we think about our cosmic neighborhood. If they don't, it will reaffirm the robustness of the cosmological principle, showing that even the largest apparent irregularities even out across the vastness of the universe. Either way, the effort to measure the universe's grand structure, to weigh the very fabric of cosmic emptiness, is one of humanity's most extraordinary endeavors. And with the powerful instruments now rising on mountaintops and orbiting above our atmosphere, we may soon find out what our cosmic home truly looks like. The future of this quest, and the decisive data that could end the debate, lies in the hands of upcoming missions, observatories designed to peel back the deepest layers of the universe's structure and reveal whether our home is truly in a cosmic hole or simply at a statistical low point in an otherwise even universe. The coming decade represents a monumental leap forward for cosmology, a time when new observatories and missions will deliver data with a precision and scope never before possible. These upcoming instruments will allow us to test, once and for all, whether we truly reside in a vast, underdense region like the KBC Void, or whether the apparent emptiness of our cosmic neighborhood is simply an artifact of incomplete observations. Among the most eagerly anticipated are the Vera Rubin Observatory in Chile and the European Space Agency's Euclid mission, both of which promise to revolutionize our understanding of the large-scale structure of the universe. The Vera Rubin Observatory, set to begin full operations in the mid-2020s, will conduct an ambitious project called the Legacy Survey of Space and Time, LSST. Over a 10-year period, the LSST will image the entire visible sky every few nights, producing an unprecedented time-lapse of the universe. It will capture tens of billions of galaxies, measure their brightness and motion, and map their distribution across roughly half the sky. Each observation will contribute to a dynamic, evolving 3D map of the cosmos, one capable of tracing the intricate weave of filaments, clusters, and voids that make up the cosmic web. For the KBC Void hypothesis, the LSST will be transformative. Its extraordinary depth and sky coverage will allow astronomers to measure galaxy density variations on scales of billions of light-years with unmatched precision. Where previous surveys, like SDSS and 2MASS, could detect large-scale underdensities only faintly, LSST's vast dataset will reveal them in exquisite detail, resolving their boundaries and structure. If a supervoid truly surrounds our galaxy, the LSST will see it. A subtle but unmistakable gradual rise in galaxy density with distance stretching across a vast region of space. Conversely, if the density remains relatively uniform beyond several hundred megaparsecs, it would strongly suggest that the KBC Void, at least as currently proposed, doesn't exist. Beyond simply counting galaxies, the LSST will also monitor Type 1a supernovae, the standard candles used to measure cosmic expansion. By observing thousands of supernovae across different distances and directions, astronomers can check whether the Hubble constant varies spatially. If supernovae closer to us consistently suggest a faster local expansion, that could lend direct evidence to the idea that we live in an underdense region expanding more rapidly than its surroundings. On the other hand, if no such spatial pattern emerges, it would point toward alternative explanations for the Hubble tension, perhaps rooted in early universe physics rather than local structure. While Rubin's LSST will paint the universe in breathtaking optical detail, the Euclid mission, launched by the European Space Agency, is already extending that vision into space. Euclid is designed specifically to map the geometry of the universe and probe the mysterious forces driving its accelerated expansion. It combines deep imaging and spectroscopy to chart the positions and redshifts of more than 2 billion galaxies, reaching out to distances of over 10 billion light-years. Its dual instruments, a visible imager, VYS, and a near-infrared spectrometer, NISP, will provide high-precision redshift data across a massive portion of the sky, offering a panoramic view of the cosmic web in 3D. For the KBC Void, Euclid's mission objectives align perfectly. Its ability to measure the clustering of galaxies and the baryon acoustic oscillation BAO scale will help determine whether large-scale inhomogeneities exist near our location. If a vast underdensity surrounds us, Euclid's data will reveal deviations in the expected pattern of galaxy clustering and gravitational lensing signals. Because it observes in the infrared, Euclid can also see through galactic dust, eliminating one of the biggest obstacles faced by ground-based telescopes, and can probe deeper into regions that may have appeared deceptively empty. Together, LSST and Euclid will provide complementary perspectives. Rubin's rapid wide-field optical survey and Euclid's precise space-based infrared and spectroscopic mapping will overlap across large portions of the sky, allowing their datasets to be cross-calibrated. Any density variations detected by one can be confirmed by the other, greatly reducing the risk of observational bias. This synergy will either reinforce or dismantle the case for a large local void with far more confidence than previous surveys could muster. And these aren't the only players in the next era of cosmic cartography. NASA's upcoming Nancy Grace Roman Space Telescope will further enhance the picture, conducting wide-field infrared imaging with exquisite sensitivity. Roman's surveys will probe dark energy, galaxy evolution, and large-scale structure with unprecedented accuracy, providing another crucial check on whether our local expansion environment is truly anomalous. Meanwhile, the Dark Energy Spectroscopic Instrument, DESI, already operational, is systematically measuring redshifts for tens of millions of galaxies and quasars, creating one of the most detailed 3D maps of the universe ever made. DESI's early results already hint at subtle density fluctuations across large volumes of space, and its final dataset will be invaluable for testing the KBC hypothesis. Beyond these large-scale mapping projects, more focused studies of peculiar velocities and gravitational lensing will help refine our understanding of the local universe's density field. For example, surveys of galaxy motion, like the ongoing Cosmic Flows project, track how galaxies deviate from pure Hubble expansion due to local gravitational influences. These flows can reveal whether matter is being pulled outward, as it would be inside a void, or inward, as near a dense cluster. Combined with lensing data from Euclid and Rubin, these measurements can yield an unprecedentedly precise reconstruction of our local cosmic environment. If these missions confirm the existence of a KBC-like underdensity, the implications would be profound. It would mean that our understanding of cosmic structure formation needs revision, and that local environment effects must be factored into precision cosmology. It might even help resolve part of the Hubble tension without requiring new physics. Conversely, if these surveys show that the universe around us is no emptier than average, it would strengthen the standard lambda cold dark matter model and focus attention on alternative explanations, such as early dark energy or new forms of fundamental particles. Either outcome would be a triumph of observational science. The void hypothesis is a perfect example of how cosmology advances, through a feedback loop of observation, theory, and simulation. A single large dataset from Euclid or Rubin could confirm or refute years of speculation, transforming a once controversial idea into either an accepted truth or a historical footnote. But beyond the data, these missions also represent something more profound: humanity's relentless curiosity about the universe we inhabit. The very fact that we can design instruments capable of detecting variations in cosmic density billions of light years away speaks to the power of reason and technology, to our species' drive to understand not just what we see, but where we are. When the Vera Rubin Observatory begins its nightly scans and Euclid's Deep Space Telescope sends back its first all-sky maps, we may finally learn whether our home galaxy floats in the heart of a colossal void, or whether the universe, even in its grandest structures, remains as uniform as the cosmological principle promises. And when that answer comes, it will mark not the end of the story, but a new beginning, a new layer of understanding about how the universe builds, evolves, and reveals itself to those who dare to look deeply enough. Now, as we approach the final reflection, one truth remains clear. Whether we dwell in emptiness or in cosmic average, our quest to know has filled the void with meaning. And it's only fitting to end this journey by looking back at what that means, not just for science, but for us. In the end, there's a quiet irony in all of this, that humanity, fragile and brief, living on a small blue world, orbiting an ordinary star, may inhabit one of the largest empty regions in the known universe. For all our centuries of looking outward, we may have been sitting in the calm center of a cosmic bubble billions of light years wide. And only now, in our technological adolescence, are we beginning to see it for what it is. It's almost poetic. The deeper we peer into the universe, the more it seems to reflect our own condition, surrounded by silence, searching for meaning in the vastness. If the KBC Void is real, it reminds us that the universe isn't built for our convenience or comprehension. It's grand, uneven, and often stranger than we imagine. Yet somehow, from inside this enormous emptiness, consciousness arose and began asking questions that reach beyond it. Perhaps that's the real beauty of this discovery, not the void itself, but our ability to recognize it. To stand in the middle of near-nothingness and still find wonder. To look out from the depths of a cosmic hollow and realize that even here, in this quiet corner of creation, we are capable of understanding the universe's grand design. Maybe, in the end, the universe doesn't need to be full for it to be meaningful. Maybe meaning comes from our awareness of the void, from our willingness to explore it, to measure it, and to find awe in its immensity. Because if we truly do live inside a cosmic whole, it's not emptiness that defines it. It's the light of curiosity that fills it. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.